Yes, thank you again, Fernando, for giving me the possibility of presenting the Motor Systems Tool in this occasion. I want to make my pointer a little bit more visible. Just a little bit about myself. Sandie Nielsen is my name. I come from Denmark, from Danish Technological Institute. I'm an electrical engineer. Been working with motors and drives since many years, and also do programming and stuff like that. After engineering school, I was an ABB employee, and with a small pit stop, I ended at Danish Technological Institute in 2002, where I have been ever since. Today as a business manager and the head of our accredited testing laboratories for motors, frequency converters, pumps, and fans, and also with strong ties to range hoods and air handling units. Since many years, I've been a consultant for Danish Energy Agency on eco-design matters on the same products. I'm quite active within the standardization world in IEC, at least level, in the groups of motors and motor systems and frequency converters. I was working at Grundfos at a period as an external trainer on pumps and pump application. And then, of course, I can do this programming mostly in LabVIEW, in which I made the MST tool. And of course, I'm also an ongoing member and task leader in the 4E EMSA platform, which is, yeah, you know about this. Yeah. So today's topic, the Motor Systems Tool. I will introduce the tool, the basic features, how it's basically working, some of the input screens and so forth, and some of the features. Talk a little bit about the models inside, and trying to exemplify how one can use it in some of the possibilities. And yeah, and hopefully you will get an interest in that, and then I will finally yeah, discuss with you Q&A, maybe some good ideas for the future and so forth. So that's basically the idea. Yeah, so let's jump into it. I made this text some years ago about what is the Motor Systems Tool, and this is an impartial calculator for complete motor systems that utilizes neutral models of standardized components to determine the efficiency at any given duty point on a complete motor system. I was actually presenting this tool in 2011 at the EMOT in Washington, D.C., and ever since we have presented it, I have presented it many times on Motor Summit and EMOTs, and even in workshops all over the world. So yeah, that's very nice. And we try to keep track on the EMSA website how many people is downloading. And I think the number these days are something like 4,500 unique downloads. So yeah, that's nice for this, I think. When you use the Motor Systems Tool, you basically need to input three basic things. I just want to start my timer here. Just a question. Yes. You have to input a load, a transmission, and then a motor/drive unit. If we go to the load profile, you have a possibility of 4 different load profiles, as we all know them. The relationship between speed and torque and power. Normally, the default is squared, such as pump and fans, but you can select the other ones as well. Then on the transmission side, you have the possibility of choosing, for instance, a belt transmission. If you choose a belt transmission, I have tried to illustrate with a little picture what kind of belt it is, and we have some standardized types. We have some standardized sizes of pulleys. We have a standardized belt ratios and so forth and so forth. And you can even select if the smallest pulley is on the motor side or on the load side. For now, the catalog of possible selectable bells would be classic V-bells, narrow V-bells, poly V-bells, flat bells, and timing bells. All of which for which we have standardized loss models depending on the degree of load. The same goes for the gear transmissions. For now, we have worm gears and bevel gears and helical gear models inside. You have to choose which type you have, and then you have to choose if you, for instance, know the nominal ETA of this gear or the efficiency of this gear, or you will have a justified guess from the program, in this case 94, and again you have to put in the output torque and speed and the ratio of the gear and so forth and so forth. That's a possibility. And then lastly, we also have recently put in a loss model from the EMCA Association, which is a fan association international, which in I think 2017 made some loss models on both belt transmissions and motors and drives and so forth. I'll show a little bit more about that later, but here you can choose their model of a belt if possible. And then of course you can choose not to have a transmission. On the motor drive unit selection, the simplest, I'm not sure it's the simplest, but at least a starting point is to input motor nameplate data. In this case, a 5.5 kilowatt motor from the European continent, 50 hertz and so forth, 4-pole. If you don't have access to your nameplate motor, or if you want to have, let's say, a calculation on as an idea of a new project or whatever, you also have the possibility of selecting from the standard sizes from the IEC tables of motors, and you can choose up to, from 0.12 to 1000 kilowatts motor here for the asynchronous side. When you have selected your motor, you also have to decide if this motor is connected direct online, if it's connected with a soft starter, or if we have a connection by a frequency converter. Until now, you can only choose PWM signal converter, but I think that's reasonable, as most converters still these days are that kind of automation. I also have a little button on the automatic slip calculation, which on the direct online is by default on. And then when you have chosen your three components of the input, you get this overview picture, the main window, I call it, where I always try to illustrate what you basically selected. In this case, you see it's a grid supplied asynchronous machine. Should be able to see that. It's 5.5 kilowatts. We have what I call the calc master at the shaft in this case, and therefore it's black, whereas the other power measures are gray. We have selected in this case a transmission, classic V-belt cocked, a ZX, like that, and we have selected a pump or a fan, this time illustrated as a fan. In terms of the calculation master, it's illustrated by, in this case, P2 and then the calculator above. And when you zoom a little bit, you can basically see the input here. In this case, it's 4.63 kilowatts. And you can basically double click with your mouse and you can change that power to 5 or 3 or 6, free of choice, of course. And as soon as you do that input, the calculation from the program will basically go in both directions in this case. So the way MST tool works in the calculation is that we always have one fixed point that we choose, in this case P2, and all other calculation origins from this power duty point with a specific power, a specific speed, and a calculated torque in this same duty point. If you want to switch your calc master, I call it, you basically push with your mouth in one of the other gray areas, and then the color changes, and then that will be your calculation master. So you can basically switch between the calculation masters dynamically at any point if you wish to do so. Other features from the main page, which is interesting, is you can change the language of the tool on the fly. In this case, it's English, but if you push the flag and you choose German for that matter, it changes the language in the entire program. I'm not sure how often you need to change a language in the middle of a calculation, but at least now you have the possibility. I should also mention, by the way, if you can see on the main window now, we have basically a calculation of the actual duty point with a 90.7 efficiency of the transmission, which leads to this power. And by the belt, we have a ratio between the speeds, so that would be 1745, and those two calculated together give this torque into the load, and we have an input efficiency on the load of 62 in this case, and therefore an output power. So we have the entire chain visible at the main window in an instant. On a direct online motor, I also have, if you selected, an automated slip calculation to give the user an idea. And the slip calculation is basically the nominal speed at full load in one end, and then almost the synchronous speed at no load, and then a straight line in between. So it's not rocket science. I have just made it like a linear relation between load and speed, and I think that's not all that bad. In this case, you can see the nominal speed of the motor is 1445 at 5.5 kilowatts, but the actual duty point is only 4.6, and therefore the speed is 1455, a little bit faster than the nominal speed, of course. Another thing on the main window, which is interesting in many cases, is actually what is the input power, and you will have a direct indication of the cost in euros. If you select that, if you push with your mouse this field down here, you get a splash screen coming up where you can indicate a number of running hours per year and also a price on your electrical power. In this case, it's euro, and I think the default value is 0.18. But the user can freely choose this, of course. And then, of course, if you have made a calculation, you have a possibility of making what I call an HTML output, kind of a visual save of the setup. If you push that button, it will create a HTML page. It will open your default browser on your Windows system. And from here, you can choose to print it, or you can save it, or whatever. But the output screen here will include the screenshots, so you can remember what you put in at the time you did. So that's one way to archive your earlier calculations. If I look here, and instead, here I'm at the system overview. If I go to the right-hand side, I also have something I call the before table and the after table. And that is basically that for each duty point like this you can add a line to the before table like this and save a line with a specific duty point, and you can indicate how many hours per year, in this case 1225 and 38, to make like a before-after calculation of two different systems, showing two different systems, but on the same kind of duty cycle in a certain process. So that would be the first tab. If you go to the right, the second tab is the after table, which is green, hopefully much more energy positive rather than the before thing. And if you fill out both of these with your duty points, that will of course take a little bit of time, then you will see an energy overview. This is an example of that, where the green and the red, the difference between the two are basically the savings. In this case, it goes from 30,000 to 28,500, so it's a saving of 1,800 kilowatt hours, just as an example. But you basically have a time duration curve that you fill out, as you see, and that's always looking at an entire year. Yeah. The next tabulation on the top is called eco-design evaluation. It's for now following the current eco-design of the fans, which is from 2011, so it's kind of old. And therefore it's very soon obsolete, because we had a publishing of a new eco-design regulation on fans on July 3rd this year, so that's fairly new. And therefore I put in this flash that I want to update this inside the MST tool within due time when the new regulation turns into force. But basically, what you have the possibility, this is the old system, of course, but you basically need to calculate if in the best efficiency point, which you have to put in, you have to know this, of course, if this specific fan would be compliant to the current eco-design regulation. This will, of course, change a little bit in the new eco-design regulation, and I will, of course, update accordingly on this page. And this is, of course, in the case of a fan, and we actually have an equal calculation if we talk water pumps, also referring to a fairly old eco-design regulation on water pumps, which is from 2012. And this regulation is, as with the fans, under ongoing review. And last week at the EMOTS in Lucerne in Switzerland, we heard from the responsible officer from the European Commission that the work is ongoing right now. They have some ISC. It needs to be cleared inside the Commission, and then it will come to voting and commenting from the MSAs around Europe in Q4 this year, and they expect to adopt and publish the new eco-design regulation on water pumps, by mid-25. What we heard last week. When this will be relevant, I will of course update this page as well in the MST tool. If I go back to the input of your motor from a nameplate, this has proven to be, I would say, interesting from my experience. What should be easy isn't always that easy, and we have had customers or colleagues calling us, writing us with strange calculations in the MST tool, which quite often could be led back to the faulty input of the motor nameplate in the tool. And of course, a motor nameplate is no easy peasy. You have to know what you're looking for, and there's a lot of numbers and so forth. What I've tried to do recently to accommodate or minimize the room for errors is that if you input a nameplate which is unrealistic, and by unrealistic I mean that the calculated efficiency is above 100, then the motor is, well, if we have that would be very good, but I think it's unrealistic, and therefore you will get a red and you will get a flashing, and you won't even be able to accept the OK button in this case. So this is trying to avoid at least some of the errors we have seen in the past from our colleagues. So basically, in this case, where I'm living in Denmark, I would use the 400 volt star connection, 50 hertz, 10.6 amps, 5.5, 0.84, and they state that it's 89.6 in efficiency at 1470 RPMs, i.e. 3. So this is the numbers I put in this box over here. My program will calculate the efficiency from these numbers to 89.2, which is almost the same as the nameplate, and I'm thinking that this is about the rounding of the numbers on the nameplate that makes that difference. I'm sure that the Siemens motor in question here is exactly spot on as it should be, of course, in the current regulation for motors. If you go to the next tab in the motor selection, motor drive selection, you can select either a synchronous reluctance motor or you can select a permanent magnet motor. We have very good input from Ghent University in Belgium, which has made some measurements in real life in their facilities and combined those with what do you call that? Manual or brochures input from manufacturers, and they have made some unique loss models for these types of machines, ranging from 0.25 to 250 kilowatts with nominal speeds from 1,000, 1,500 and 3,000 RPMs. So if you want to choose a motor like that, you just have to put in the nominal RPM and also the kilowatt size, and then you will let the MST tool handle the rest from that point. The next tabulering is from the IEC standard called 61800-9-2, which is also a thing that I'm a part of. In the version here, which is from 2017, there was some loss models in Annex A and in Annex D. And if someone had an interest in calculating on these specific loss models, this was your possibility. I think these loss models are close, if not already, they are at least close to being obsolete because we have an updated loss model or interpolation model just published this year in the 60034-2-3. And this is also a thing I need to put in the MST tool within a reasonable amount of time. So maybe I will replace these old IEC models or even just add a new tab, which is, either. And the last tab on the input motor thing is from the AMCA standard, as mentioned. It's from 2017. I'm not aware if it has been updated since. But in the AMCA standard, you have EBCA nominal motor 60 hertz in horsepower. You have the same in kilowatts. You have the IEC tables for 50 hertz and the IEC table for 60 hertz, and you even have a loss model for the Chinese standard called GB 18613, which is from 2012. I'm not aware if any of these have been updated since. If that's the case, I would of course like to hear that from AMCA, and then we will see if we need to update anything. At this point, or at the time we made this, it was at least up to date in terms of the current standard here. So that's also a thing you can use in your calculation. So what can we use the MST tool for? And this I will try to answer with a couple of examples. The first example is a pump application. This pump application comes from a real-life exercise a colleague of mine was on. One second. It was an asynchronous motor with a known nameplate. That means it was readable. There was no transmission, and we were actually, in this case, able to measure both the flow and the head and the input power of the machine. So that would be what I would call an easy peasy case, but still it's interesting to put it into the MST tool to get some of the, I would say, underlying calculation results. So what we basically got was a sheet from the plant owner, and the first pump we wanted to look at was this one, We call it P1. We have some numbers for the motor. It's a 90 kilowatt motor, 2-pole machine, 92 amps, boom, 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 boom. Should be 95 in efficiency according to this. And it also seems to be from 1998, which is, well, old motor, but old in this case is not the same as bad. So this was the information we had, and that means that I basically put those numbers in at the asynchronous motor tabulering. 90, 660, 92 amps, 0.191, 50 hertz, and 2970. And from these numbers, I can calculate, of course, the nominal torque of the machine and also the nominal eta. And the nominal eta is, of course, calculated from the output shaft power, 90 kilowatts, divided by the voltage times the amps times the volts phi, the power factor, times square root 3 as the input power. Very simple. So it's 94 according to the nameplate. And when I input our measurements, which we found at the site, I basically go to the application calculator. I choose water pump in this case. In the application calculator on the water pump side, it will be this formula, which is a standardized SI formula for hydraulic power. The 4 inputs to that would be the flow. In this case, it would be 120 cubic meters. It would be the head of 141 meters. It would be the density of the water, 998.2, and it would be the gravitational constant, in this case, 9.82, as usual. If you look at the main screen of the tool in the back, we basically see the motor that I put in before. I have pushed in this area with the mouse to change the calculation master to this point. And I double click this area and I write by hand 82 kilowatts because this number is what I actually measured at the site. So by knowing the nameplate of the motor and knowing the input power to the motor, the model inside the MST tool calculates an efficiency in this duty point of 94.2. And if that's the case, then the shaft power must be 77.2. We also calculate, or the MST tool calculates a speed in this case on 2974 because the nominal speed is 2970 at 90 kilowatts. And when it's not 90 kilowatts, it'll be a little bit faster. So this is the calculated speed, and those two calculated gives you an output torque of this. And when you know this output torque, you can also easily calculate the load of the machine in this case, which is 85.7. But what's also interesting is the way that the MST tool calculates, namely from right-hand side towards left, in this case, 94. We have the shaft power, 77.2. We have no transmission, so we still have 77.2 going into the application, in this case, a water pump. So when you push the P4 calc down here, this splash will come up, and there I will have the 77.2 from before put into the model. And then when I fill in these 4 numbers here, I calculate the hydraulic power to 46.05 in this case. And when I know this number and I know this number, the division is quite easy, and therefore I can, without having a pump curve, see that the efficiency of this pump would be around 60%. The speed in this case comes from the motor calculation, 29.74. And finally, you can see the annual cost here is 62,730, and this number comes from 4,250 hours per annum. It summarizes to 348.5 megawatt hours, 0.18 euros, and that gives the 62,000. The number of hours came from this, from the plant manager here, hours per year. So, in conclusion, from a very little input, you can basically calculate and understand an entire pump system. what is your flow, what's your efficiency of the pump, and so forth. And you can even use it if you have access to your pump curve. It's actually possible because now you know the shaft power, so you can basically go into the pump curve and basically have a good estimation of flow and head of the pump. So you don't, if you don't have access to that, that would basically give you, well, at least an idea what the flow would be if you know the pump, if you have the pump curve. So quite efficient, I think, in my mind, at least. The next thing I want to show you, the last thing in this case, is an interpolation exercise where you have access to an entire fan curve in this case, and you deduct 12 points from that. Again, we have a standard I2 asynchronous motor. This time we have a VSD included because we want to change the speed of the application. I don't have a transmission, which would be, make no sense when I have a VSD. And of course, it's a fan application with a fan of which I have a quite detailed curve available. So again, I start by resetting the tool and then input the asynchronous motor. In this case, I just by heart know it's a standard IC motor. I chose 11 kilowatt IE2 and a 4-pole machine. From the IC tables, this must be 89.8 at the nominal load point. So this is what is calculated. And I also choose the VSD on the machine. When I put this in, I come to my main window again. By default, the MST tool will always select, if you don't choose something else, it will always select the nominal power at the shaft. If that's the case, then it's calculated to 88.5 in the model due to the frequency converter, which would give us 12.4 at the input power to this motor in this case, or to the frequency converter in this case. Again, we don't have a transmission, so we have 11 kilowatts on the other side of transmission, on the input to the fan. First hand, the default efficiency of an application in MST tool is 65, and therefore the hydraulic power of the fan is 7.15 in this case. But that's not really correct, and we know this, and therefore we push the P4 calc button. I have enhanced it here just to make sure that everybody understands. This is what I push. And when I push that, I go into the application calculator. As before, you can see I have the possibility of choosing a water pump. I also have the possibility of a fan, which is a simpler formula, again, with inputs, possible inputs as before. You can always also choose a hydraulic pump. You can choose a compressed air, or air compressor, or a cooling compressor, or something I call other duty. Unfortunately, we don't have time to go deeper into these exercises today, but maybe on another occasion we can show an example on that. For now, I will use the fan exercise, and fortunately, I have available a quite extended map of the fan and the trade of this fan. And for you people who are not used to looking at this, we basically have the flow on the x-axis, we have the delta P on the y-axis, we have these black curves here. It's 1,000 RPM. This is 1,100 RPM. This is 1,200 and so forth. And as it's a 4-pole machine, the area up here is gray because this would be overspeed. Going down from this top down in this direction is actually the efficiency curves. 80, 82 comes down in this direction, 82 again in this direction, and 80 in this direction, and 70 over here. So there's basically a maximum of efficiency on this fan in this area here. You also have indication of the noise coming from the fan by decibels, and you also have an indication on the kilowatts, and I would assume these kilowatts would be the input required to the fan. But let's see. So what we want to do in this application calculator, we basically want to define 12 duty points from which we will calculate, extrapolate, interpolate other duty points. And this is, in this case, chosen quite straight with the same pressure, four different flows times 3. So that gives me 12 duty points. I call it representative duty points in this case. So I will tell MST tool, this is my points. I can tell that by manually putting them in by hand like this. And then I can save the file and I can reopen it and I can clear the table and so forth afterwards. But it's basically two independent relationships between flow, delta P, and speed, and flow, delta P, and efficiency that I put in. When I have put this in, I can choose a, let's say, desired duty point. In this case, I want to reach something which is 8 cubic meters per second on the flow, and I want to have a delta P of 900 pascals in this duty point. And visually, of course, I can see both the speed and the so forth, but I also would like to have MST tool calculate this for me. And that's what I have done in this splash. When I chose on the application calculator, I chose the fan. I chose the input data. When I chose this one, this is where you have this table you can input. If you have done this and you push the load profile on like this, then you input your desired duty point, in this case, an airflow of 8 cubic meters per second and a pressure of 900 pascals. And when you do that, the two results from the calculation is the green boxes down here, a calculated efficiency of 81.36 and a speed of 1183. And if we look at the graph just to check if this sounds reasonable, if we start on the efficiency, the line for 80 is here and the line for 82 is here. And then we can see the green dot is more than 81, but it's not 82. And we have a calculation of 81.36. I think that sounds reasonable. And on the speed, which is the black curves, this is the 1400 curve. This one is the 1300. This is the 1200. And I can see that I'm a little bit below 1200, but much closer to 12 than to 1100. And the calculation is 1183. So I think also that sounds reasonable. So now we know the output power in hydraulic power coming from these two numbers. We know the efficiency and we know the speed. And when we know all those things, it must be that we have an input to the fan of 8.85 due to the efficiency and so forth. So pushing OK, we come back to the main window of the MST tool. We have the values transferred into the main window, namely the 7.2, the 81 point. It was 36, but here it's rounded and so forth. And then we can see we now have a shaft power of 8.85 on the motor shaft, as we just calculated. We have this at a speed of 1183 as calculated. And if this is the case, the motor systems tool will calculate an efficiency of the motor and drive combined to 87.2. And if this is the case, the input power must be 10.2 kilowatts. And again, we have down here an estimated cost of this, depending on the hour and of course, depending on the price that you put in on your on your kilowatt, your kilowatt hour price in your country you live in. So I hope this will illustrate how it is one possible solution to have if you have a known load and loss curve, efficiency curve of a fan or a pump. It could also be something different. There's no requirement that it needs to be flow and delta P. And then you can have the MST tool to basically, calculate your system. So that's basically what I wanted to show today. I want you hopefully to remember that the Motor Systems Tool, MST tool, is a dynamic tool which I want to continuously develop. I do that within the EMSA umbrella. And as examples, we saw today that I have to do some work now in terms of the upcoming eco design on both fans and pumps. Most likely also on the new interpolation, extrapolation model from the IEC world on motor systems. I can also say that we have other tools. We don't have time to show them today, but maybe on another webinar, we could demonstrate some of those. So we basically now have a family of tools on the EMSA webpage covering air compressors, vacuum systems, hydraulic systems, and very soon we will also have ventilation systems in entire buildings. I will say that you can find the tools, of course, at our webpage, which is listed here. Updated versions of the tools will soon be released. Unfortunately, we did not manage to do it prepared for today, but we will very soon update them. We will have new guides, new examples, and so forth. And also we have created an expert pool of experienced users of the tool, like myself, but we are 6 persons in total. If you want to send a mail to all of us with a widespread, so to speak, you can write us on the Hotmail, which is MST mail address as listed here. Last thing I want to do is say that I would encourage you to sign up for our newsletter at the EMSA platform. Then you will have what's new in the motor world. I think we send it out 3, maybe 4 times a year, 2, 3, or 4 times, depending on if we have news to tell about. Yeah, and I think that's it. Thank you for listening, and yeah, write me a mail if you have something. But for now, I think we go to the Q&A.